So in this next lesson, we're going to continue solving polynomials. But what we're going to find is we can't factor all the way. We're going to be required to use the quadratic formula. So our first example here looks like the examples we saw from the first video, lesson 3.2a. So let's start approaching it that same exact way. I expect 3 solutions because my largest exponent value is a 3. And my first question that I ask is there anything that every term has in common? It looks like all the numbers are divisible by 2, and it looks like every term has at least one multiple of x in it. So a 2x is what I'm going to pull out of every term. 2x out of 2x to the third leaves me with x squared. 2x out of negative 4x squared leaves me a negative 2x. 4 divided by 2 is the 2. X squared divided by x is the x. And lastly, if I divide 2x out of 26x, I believe that leaves me with a negative 13 and no x. And all of that equals 0. So 2x times x squared minus 2x minus 13 equals 0. So here's where things get a little different. Because if I look now, normally what I would do is I would then try to take this remaining quadratic and factor it into 2 separate pieces, 2 binomials, to further factor it, but I can't. Because is there any set of 2 numbers that multiply to negative 13 and add to negative 2? Well, there probably are, but good luck finding them. They're really nasty decimals that are going to actually accomplish that. So, or potentially imaginary numbers that are going to accomplish that. So we can't factor anymore beyond this. But let's use some of the reasoning. We know we expect 3 solutions, and normally doesn't a quadratic break up into the 2 pieces and we get 1 solution from each of those pieces? So how many solutions do we expect to get from this quadratic piece left? We expect to get 2 solutions. How many solutions do we get from this x that we already factored out front? We get 1. Well, isn't that my total of 3 solutions that I expect? So right off the bat, I know that x equals 0 is one of my solutions. That comes from this factor right here. If I plug 0 in for x, that makes the whole left side of the equation 0, which makes my equation equal to 0. So one of my solutions is 0, but I know I have 2 more solutions that come from here. I need to know what makes x squared minus 2x minus 13 equal to 0. Well, I can figure that out using the quadratic formula. X equals negative b plus and minus the square root of b squared minus 4ac all over 2a. So let's use that. I know that the 2 solutions, the 2 values of x that make this equation equal to 0 are x equals negative b. Well, b is already negative 2, so that takes me to a positive 2. Plus and minus the square root of b squared. Negative 2 squared, remember whenever you square a negative it's positive, so that's going to be a 4 minus 4 times a, which is 1, there's a 1 in front of the x squared, times c being a negative 13. All of that's divided by 2 times a being a 1. So simplifying this, now we don't want decimal approximations. No decimal approximations. We want exact. So all we need to do is simplify as far as we can. So that's going to be a 2 plus and minus the square root of, in my calculator really quick, I'm going to do 4 minus 4 times 1 times negative 13, and I'm getting a 56. And all of that's divided by 2 still. Okay, can I simplify further? I believe I can. Let's look at that 56. Can I break the 56 up? I can break the 56 up into 4 times 14. The 4 splits up into 2 and 2. The 14 splits up into 2 and 7. Do I have any pairs? I have a pair of 2's. But then the 2 and the 7 here don't have anything to pair up with. So they stay underneath, but what comes out? A 2 comes out. So that's x equals 2 plus and minus 2 times the square root of 14 all over 2. Great, so I simplified the radical. Can I simplify even more? I can. If I look at all three terms, as we saw from homework packet 3.1, if all three terms have something in common, which they do, they all have 2 in common, I can divide the 2 out of everything. So 2 divided out of 2 was a 1, plus or minus 2 divided out of 2 root 14 is just the root 14. And then in the bottom, 2 divided by 2 is a 1. Divide by 1 doesn't really mean anything, so I don't need to put it. So what are the other two solutions? My other two solutions are 1 plus root 14 and 1 minus root 14. But it took the quadratic formula to get those two other solutions. So the 0 came from the factor out front, and the 1 plus root 14 and the 1 minus root 14 came from the quadratic that wasn't factorable. I had to use the quadratic formula to find those other two solutions. And now here are my three solutions that I expected to get because I had a highest exponent value of 3. So let's look at this next example. I can first tell, number one, I'm going to have 4 solutions because I have an x to the 4th. But I can also tell I'm going to have to manipulate this a little bit because it's not set equal to 0. And I need it set equal to 0 if I'm going to solve. So I'm going to add the 25x squared to both sides and get x to the 4th minus 8x to the 3rd plus 25x squared equals 0. Now that I'm set equal to 0, I can start the process of factoring. First question, is there anything every term has in common? No numbers because it's just a 1 in front here, and 8 and 25 don't have anything in common. But each term does have an x squared in common. So let's factor that out. X squared out of x to the 4th is x squared. X squared out of negative 8x to the 3rd is negative 8x. X squared out of 25x squared is 25. And that equals 0. So normally, as we saw, we would try to factor this into 2 different binomials. But if you try that, you'll fail, unfortunately, because it's not factorable. Okay, so I know I'm supposed to get 4 solutions. Here's a quadratic. I know in a quadratic I expect 2 solutions. Can I expect 2 solutions from the x squared? Well, what do I plug into x to make x 0? Well, I plug in 0 to x to make x equals 0. However, remember what we saw, how the x squared can really be written as x times x? So how many zeros are there, or x's, can I plug 0 into? 2. So x equals 0 has that multiplicity of 2. It counts for 2 of my solutions, but then the other 2 solutions come from the remaining quadratic piece. Well, in order to find the 2 solutions from the remaining quadratic piece, that's x squared minus 8x plus 25 equals 0, I've got to use the quadratic formula. X equals negative b plus and minus the square root of b squared minus 4ac all over 2a. So let's do that. X is equal to negative b. B is already negative 8. So negative 8 is positive 8. Plus and minus the square root of b squared. Negative 8 squared is positive 64. Squares undo negatives. Minus 4 times a, which is 1, times c, which is 25. And all of that's divided by 2 times a being a 1. Okay, so now we have to simplify. X is equal to 8 plus and minus the square root of, I'm going to do 64 minus 4 times 1 times 25. And I'm getting a negative 36. All of that's divided by 2, the 2 times 1. Now, you'll notice we've got a negative under our square root. How do we deal with that? We know that any time we have a negative under our square root, that implies the imaginary solution. So we can get rid of the negative under the square root, but what pops out right in front of the square root? The imaginary I, imaginary number I. So that's 8 plus and minus I times the square root of positive 36. Remember, popping the I out gets rid of the negative, all over 2. But what do we know the square root of 36 is? We know the square root of 36 is 6. So this becomes 8 plus and minus 6I all over 2. Now it looks like there's one more step we can do because both the 8 and the 6 can be divided by 2. So this turns into x equals 8 over 2, which is 4, plus and minus 6I over 2, which is 3I. So the two solutions that come from this quadratic piece here that I could not factor, well, it couldn't factor them because the solutions were imaginary. Those two solutions being 4 plus 3I and 4 minus 3I. So here's my 4 solutions. 2 of them are imaginary, and then the other one is 0, but because that 0 had a multiplicity of 2, it counts for 2. So there's my 4 solutions. So there's some special case polynomials that we want to take a look at now, specifically the sum and difference of perfect cubes. So sum and difference, two separate equations. Here's the sum, that's addition, and here's the difference, that's subtraction. The sum and difference of perfect cubes. Okay? So what I have is a formula that shows me how to factor the sum and difference of two cubes. So let's look at this first example. This first example is a sum, so it's this top equation that I'm going to be using. But how do I do that? Because I see an x to the third plus, but then I just have 27. But what we have to realize is that that can be written as x to the third plus 3 to the third. Because 3 times 3 is 9 times 3 is 27. 27 actually is a perfect cube. And that equals 0. Now we want to be able to factor this so that we can solve it. This formula right here tells me how to factor it. Okay. Now in this case the a is actually my x and the b is 3. So here's what it looks like in factored form. It's a, which for me is x, plus b, which is 3 for us, times a squared. So for us that's x squared, minus a times b. A times b, that's x times 3. I'm going to write that as 3x, plus b squared. b is 3. 3 squared is 9. So this right here, the sum of two perfect cubes, factors into this right here. Now it may not seem like it helped us to solve this, but it did. Okay, it put us in factored form. Because how many solutions do we expect? We expect 3 solutions. So I need it to break up into 3 factors. Well, I've broken it up into 2 factors here, but isn't this a quadratic? So can't that piece be broken up more? What we'll find out is that with the sum and difference of perfect cubes, that second quadratic piece cannot be factored, so the quadratic formula is going to be required to be able to solve for that. So let's see what that ends up looking like. I know from this first piece, I know I should have 3 solutions. From this first factor right here, I know one of my solutions is negative 3. Because negative 3 plus 3 here is a 0. But then, what about the x squared minus 3x plus 9 equaling 0? Well, quadratic formula. X equals negative b. b is already negative, so that brings it to a positive 3. Plus and minus the square root of b squared. So b is negative 3, so b squared is positive 9, minus 4 times a, which is the 1 right here, times c, which is 9, all divided by 2 times 1. So x is equal to 3 plus and minus the square root of, in our calculators, let's do 9 minus 4 times 1 times 9. And I'm getting a negative 27. Negative 27, all divided by 2. Negative under a square root, we know that means it's 3 plus and minus I times the square root of positive 27, all over 2. The negative disappears from underneath the square root, and the I pops out. But can the square root of 27 be reduced? I believe 27 is 3 and 9. The 9 breaks up into 3 and 3. I do have a pair of 3's, so a 3 comes out. But I have this 3 right here not paired up with anything that's going to stay under. So this becomes x equals 3 plus and minus 3i root 3 all over 2. Now, does each term here have something in common? Unfortunately not. These do, but that one doesn't. They all have to have something in common to continue the simplification process. So this is where we stop. So we know our other two solutions are 3 plus 3i root 3 over 2 and 3 minus 3i root 3 all over 2. So here are the 3 solutions I expect to get from solving this original polynomial, which is the sum of 2 perfect cubes. We can't factor it without knowing that formula. So let's try this special case one more time. You'll notice here that instead of the sum, I have the difference between two things. The question is it the difference between 2 cubes? Because in this formula, I have a cubed minus b cubed, right? So I see an x cubed here, so it's hinting at that this formula is going to be useful. The question is, can I rewrite all of the constant numbers in terms of cubes? Can I rewrite 8 as something cubed? And in fact, I can. 2 cubed, because 2 times 2 is 4, times 2 is 8. So 2 cubed is 8. So I can rewrite this as 2 cubed times x cubed minus, now the 64. 64, I think I can rewrite that as 4 cubed, because 4 times 4 is 16, times another 4 is 64. So 4 cubed is 64. So and that all equals 0. So the way I can then rewrite this is, since both the 2 and the x have the same exponent of cube on them, I can write it as 2x cubed minus 4 cubed. So now I have this setup right here where the a value is 2x and the b value is the 4, because it's 2x cubed minus 4 cubed. So when I write it out in factored form like this, my a is 2x and my b is the 4. So what would this look like written out? It would look like a, which is 2x, minus b, which is 4, times a squared, so that's 2x squared, plus a times b. That's 2x times 4, which is 8x, plus b squared. b is 4, 4 squared is going to end up giving me a 16. And this actually all equals 0. So I've factored the difference of 2 cubes. I'm going to clean it up a little bit and write it as 2x minus 4 times 2x squared. That squared belongs to the 2 and the x. So that's 2 squared, which is 4. It's going to be a 4x squared plus 8x plus 16 is equal to 0. So I've taken this 8x to the third minus 64 and I have factored it out. Now I notice that I've got a factor here, which I'm going to get one of my solutions from. The question is, what do I plug in for x that makes this 0? I think if I plug a 2 in for x, because 2 times 2 is 4, and 4 minus 4 is 0. So if I plug a 2 into the x here, that makes that 0, which makes the whole thing 0. So there's one of my solutions. But I know because it's an x to the third equation, I'm going to expect 3 solutions. So there's 2 other solutions that I expect, which makes sense because here I have a quadratic, an x squared, which I know 2 solutions are going to come from. However, anytime you use these formulas here for the sum and difference of 2 perfect cubes, this quadratic piece here is not going to be factorable. In fact, it's always, always, always going to give you imaginary or complex solutions, which means I have to use the quadratic formula. X equals negative b plus and minus the square root of b squared minus 4ac all over 2a. So that's going to be x equals, let's see, my a is 4, my b is 8, and my c is 16. So that's going to be a negative b, so that's negative 8 plus and minus the square root of b squared. B is 8, 8 times 8, 8 squared is the 64, minus 4 times a, which is 4, times c, which is 16. And all of that's divided by 2 times a being the 4. So what do I have here? I have x is equal to negative 8 plus and minus the square root of, okay, let's do 64 minus 4 times 16. And I'm getting a negative 192. And that's all over 2 times 4, which is 8. So I have a negative under the square root, which means negative 8 plus and minus I times the square root of 192. So I remove the negative from underneath the radical and put the imaginary number out front. But now I've got to consider this 192 thing. Okay, 192, what can I split it up into? I think I can split it up into 48 and 4. The 4 here can split up into 2 and 2. 48 splits up into 12 and 4. This 4 splits up into 2 and 2. A lot of doubles here. The 12 splits up into a 4 times 3. And the 4 splits up into a 2 times 2. I have 3 pairs of 2 here. 3 pairs of 2, which means 3 2's come out. 2 times 2 is 4, times 2 is 8. So an 8 comes out of this radical. That's going to be x equals negative 8 plus and minus 8i times the square root of, I've got that 3 left over, all over 8. Good, so I've got the radicals simplified. Last but not least, every single term here, the negative 8, the 8i root 3, and the 8 in the denominator, they all have an 8 in them. So I'm going to divide 8 out of every term and get x equals, let's see, negative 8 divided by 8 is negative 1, plus and minus 8i root 3 divided by 8 is just I root 3. And in the denominator, the 8 divided by 8 goes to 1, so I don't need that in the denominator anymore. So my other 2 solutions to my original problem right here, I had the 2 from this first factor, but the 2 other solutions that come from this quadratic here are negative 1 plus I root 3 and negative 1 minus I root 3. So there's my 3 solutions after using the difference of 2 cubes formula to factor it and then solve from there.